If you ask someone on the street for directions to the nearest coffee shop, they don't usually look at you and say, well, put your left foot forward, shift your weight, now flex your knee 20 degrees.
Right, that would be terrifying.
Yeah.
And, completely exhausting. They just say, take a left, it's the brick building.
Yeah, exactly. They give you the layout, and they just trust your brain to figure out the actual physical mechanics of getting there.
Yeah, they don't micromanage your joints.
But for decades, I mean, we forced computers to do exactly that. We communicated with them using that exhausting foot-by-foot method. But today, we are looking at a completely different paradigm. So welcome to another deep dive, specially tailored for you, the learner. Today, we're skipping the dense academic textbooks and jumping straight into a really fascinating source, a comprehensive Wikipedia article on logic programming.
It's a great piece.
It really is. And the mission of this deep dive is to extract the absolute best nuggets from this text. We're going to demystify what logic programming is, explore this dramatic history behind it, and uncover how it actually mimics human thought and human law.
Yeah, and the goal today is really to look at the why behind the code. Not just how it works, but why this approach even exists and why it matters.
Okay, let's unpack this.
Yeah.
Because before we can understand why this sparked an actual academic war, we need to know how it actually works.
Right. So the fundamental shift here is moving from procedural to declarative programming.
Declarative, meaning?
Meaning you don't give the computer step-by-step instructions. That foot-by-foot method, that's procedural. You're dictating the control flow. But logic programming is declarative. You just give the computer a set of sentences in logical form, facts and rules, and you just let it figure out the solution.
So you're just describing the problem, basically.
Exactly. You describe what the problem is, not how to solve it. If you look at the structure of a rule in this system, it looks sort of backwards. You write the conclusion first, so let's say conclusion A. Then you write a colon and a dash, followed by the conditions, let's call them B and C.
Wait, a colon and a dash, like a sideways smiley face.
Yeah, a lot of people see that. But think of that colon and dash as the computer's way of saying the word IF. So it translates to A is true, IF, B, and C are true.
Oh, I see.
Yeah, and A is the head of the rule, the goal. B and C are the body. And these are known as horn clauses.
Horn clauses.
Right, which is just a formal way to describe rules that have one clear, definite conclusion. And if you just have A with no conditions, that's just a fact. Then you just ask the system queries, and it does the deduction.
Okay, let me try to make this concrete using the family tree example from the source text.
Sure, go ahead.
So if I tell the computer, Charles is William's parent, that's a fact, right?
Yep, a base fact.
And then I give it a rule, like a grandparent is a parent of a parent. In a normal procedural language, I'd have to write a loop to search the whole database, hold it in memory, cross-reference everything.
Which takes a lot of manual coding, yeah.
Right. But here, I don't need to write a loop. I just ask the query, who is William's grandparent? And the computer does the logical heavy lifting. It just connects the dots.
That is the exact elegance of it. It searches its database of horn clauses and figures it out.
So if it's that elegant, I mean, why wasn't this the only way we programmed computers from the start?
Because it caused a massive academic rivalry.
Really?
Oh, yeah. In the late 1960s and early 1970s, the AI community was completely split. On one side, you had the declarative camp.
Which our sources say was mostly Stanford and Edinburgh, right?
Right.
With guys like John McCarthy, Cordell Green, Robert Kowalski.
Exactly. They believed knowledge should be represented logically. But on the other side, you had the procedural camp, mainly at MIT.
Ah, MIT. Marvin Minsky and Seymour Papert.
Right. And they wanted step-by-step control. They looked at pure logic and thought it was way too inefficient for real-world computing.
Wait, so you're telling me that one of the most important programming languages in AI history, Prolog, basically emerged because two rival academic factions couldn't agree on whether to give computers rules or instructions?
That is exactly what happened. The declarative camp wanted mathematical purity, and the procedural camp wanted control, using things like backtracking, where the computer tries a path and rewinds if it hits a dead end.
Like a maze.
Yeah, exactly like a maze. But the two sides finally reconciled thanks to Elaine Kolmorauer and Robert Kowalski.
This was in Marseille, right? Around 1971 or 72.
Yes. Kolmorauer was working on a French question-answering system. He invited Kowalski over, and together they realized you could actually execute pure logic as a controlled series of steps. They combined the two philosophies.
Wow.
And that reconciliation led directly to the creation of Prolog in 1972.
Which stands for Programming in Logic.
You got it. And this whole reconciliation led to a really fundamental realization about problem solving, which Kowalski actually captured in an equation.
Algorithm equals logic plus control.
The equation of the century, some call it. It means any algorithm has two parts. The logic is the knowledge, the rules and facts, and the control is the strategy the machine uses to process it.
So logic is knowing the recipe for a cake, and control is whether you start by gathering the ingredients, which the text calls forward reasoning, or visualizing the finished cake and working backward to find out what you need, which is backward reasoning.
That's a perfect analogy. Backward reasoning is top-down, like Prolog uses. It reduces goals down to base facts. Forward reasoning is bottom-up, deriving all possible facts from the base.
Does it really make a big difference which one you use?
Oh, absolutely. The text uses the Fibonacci sequence to show this.
Oh, right, where each number is the sum of the two before it.
Yeah. If you use backward reasoning to find a large Fibonacci number, the computer starts at the top and says, okay, I need n-1 and n-2.
And then for n-1, it needs n-2 and n-3, so it's calculating n-2 twice.
Exactly. It redundantly calculates the same numbers over and over. It's exponential complexity. The computer will just crash.
Yikes.
But if you just change the control to forward reasoning, keeping the exact same logic, it starts at 0 and 1 and just adds them up linearly. It takes almost no time at all.
Wow, so no recomputation. It just walks up the sequence. But real life isn't a neat math problem with perfect facts. How does it handle missing information?
That is where we get to a concept called negation as failure.
Negation as failure.
Right. In this paradigm, if the computer cannot prove a positive condition is true, it just assumes it's false.
Here's where it gets really interesting. Doesn't this mean the computer's just jumping to conclusions based on ignorance? Is that safe?
Well, it makes it a non-monotonic logic, meaning conclusions can be withdrawn when new information appears. It's highly adaptable.
Can we use the Tom the Thief example from the article?
Let's do it. So say we have a rule. A person is punished if they're a thief unless they are a minor.
Okay.
We tell the system, Tom is a thief. It checks if he's a minor, finds no evidence of it, so it assumes he's not. Verdict, Tom is punished.
So it jumped to that conclusion.
Yeah.
But then what if we learn he's 15?
We input that fact. The system immediately withdraws the punishment conclusion because now the minor condition is met. The new verdict is Tom is rehabilitated.
And if we learn he's a violent offender?
We add a rule that violence defeats rehabilitation. The system reevaluates, the exception triggers, and the punishment is reinstated.
It's just arguing with itself. It's bouncing between rules and exceptions.
Exactly. And that exact tendency to jump to conclusions and revise them later isn't a flaw. It actually perfectly aligns with how the human brain works.
Really?
Yeah, cognitive scientists like Paul Thagard and Keith Stenning, who are cited in the source, argue that this is psychologically plausible.
Because humans use defaults and exceptions all the time.
Right. If I say bird, you assume it flies. If I say penguin, you pull up the exception. You don't crash. And Stenning even says this kind of backward reasoning has an appealing neural implementation.
That makes total sense. So instead of writing endless if-then loops to cover every single edge case, we are basically giving the computer a law degree, like feeding it the civil code and letting it argue with itself to find the verdict.
That is quite literally what they did. In the 1980s, they digitized the British Nationality Act using logic programming.
Oh, wow.
And today, Japan has a modern system called Prolog.
Right, the Prolog-based legal reasoning system.
Yes. And it uses roughly 2,500 rules from the Japanese Civil Code. It models human legal arguments perfectly.
But wait, if it's this good, why did it kind of fade out? The text talks about the Japanese fifth-generation computer systems project, the FGCS, in the 80s.
Yeah, they poured massive money into trying to use concurrent logic programming for parallel AI, meaning multiple processors working at the same time.
But it failed.
It did. It turns out forcing logic to commit to choices in parallel hardware ruined the mathematical purity. It introduced timing bugs. And meanwhile, regular general-purpose computers just got incredibly fast.
So standard procedural programming just outpaced it in raw speed.
Exactly. It couldn't compete.
But the paradigm didn't die, right? Because the source text goes into how it's splintered into these modern flavors, like Datalog.
Right, Datalog is huge for databases. Standard relational databases like SQL choke on recursive queries like finding an ancestor 15 generations back.
Because it doesn't know how many times to loop.
Exactly. But Datalog handles recursive rules natively and efficiently.
And then there's ASP, answer set programming. The text describes it as a generate and test method.
Yes, ASP is amazing for constraint problems. Take map coloring. You need to color a map red, green, or blue, but no touching countries can be the same color.
Procedurally, that's a nightmare of checking every single border.
But in ASP, you just generate every possible color combination for the universe and then apply a constraint test to filter out any maps where touching countries share a color.
Generate the universe, then destroy the ones that break the rules. That is wild.
It's incredibly powerful.
But the last one mentioned is inductive logic programming, or ILP. And this one flips the script completely.
It does. ILP is a form of machine learning. Instead of giving it the rules, you give it the facts and the answers, positive and negative examples, and you make the machine learn the rules.
If inductive logic programming is about inducing the general rules from a bunch of positive and negative examples, isn't that essentially exactly how you or I learned what a dog or a car was when we were toddlers?
It's exactly the same mechanism. You show a kid a dog, say dog. Show a cat, say not dog. Eventually, they induce the rule of what a dog is.
That's fascinating.
And Stuart Russell, a major AI researcher, notes in the text that this kind of concept invention is key to reaching true human-level AI.
Wow. We have covered so much ground today. From the simple idea of just giving computers declarative rules to the academic turf wars at MIT and Stanford, all the way to modeling the Japanese civil code and mimicking toddler cognition. So what does this all mean? Where does this leave us today?
Well, it leaves us with a really important thought to mull over. Right now, our modern AI, like massive neural networks, they're incredibly powerful, but they're completely unpredictable black boxes.
Right, they just guess based on statistics.
Exactly. So if logic programming so closely mirrors human cognitive rules, defaults, and the legal system, might the future of AI require us to combine our modern neural networks with this classic rule-based logic programming?
Just to keep the AI's reasoning explainable.
Explainable and actually aligned with human law.
Blending the statistical guessing with an actual logical law degree. Love that.
Love that.
Well, be you the learner. Thank you so much for joining us on this deep dive. Stay curious, keep questioning how things work, and we'll see you next time.